The electric arc hisses and spits molten metal across the frozen French countryside. Sergeant Frank Kowalski steadies his hand, watching the nickel-based welding rod fuse a 2.5-inch armor plate to the glacis of an M4A3 Sherman. It's January 14th, 1945, in a makeshift field workshop outside Metz. The temperature hovers at -8 degrees Celsius. His hands shake, but not from the cold. 3 days ago, his battalion lost 11 Shermans to German 88mm guns in less than 20 minutes. The math was simple and brutal. Standard Sherman frontal armor, 2 inches thick at 56 degrees, offered approximately 77mm of effective protection. The German 88mm WK-36 gun could penetrate 138mm of armor at 500 meters. The equations didn't balance. Men died in the gap between those numbers. General George Patton stands 15 meters away, arms crossed, watching the welding operation with an intensity that makes every man in the 3rd Army Ordnance Battalion nervous. He's just issued General Order No. 47, countermanding his own directive from 6 months earlier. In the summer of 1944, Patton banned all improvised armor modifications, calling sandbags and concrete useless weight that breaks suspensions and wastes fuel. Now, in January 1945, facing renewed German counteroffensives and the most heavily armoured panzers of the war, he's ordering something different. Something that military procurement regulations technically classify as unauthorized field modification of government property. Take armour from knocked-out tanks, cut it free, weld it onto operational Shermans. Use enemy armour if you find it. Do whatever keeps crews alive. Kowalski adjusts his welding helmet and makes another pass. The salvaged plate, cut from a destroyed M4A3 that took a direct hit near Bastogne, glows orange where the electrode meets steel. This isn't standard procedure. It's not in any manual. The welding specifications for armor plate require controlled environments, specific preheat temperatures, post-weld stress relief. Kowalski is working in sub-zero conditions, using portable generators, joining plates that were never designed to be welded in the field. If he gets it wrong, the weld will crack under the thermal shock of the next 88mm shell. Spalling will send fragments through the crew compartment. Men will die from his mistakes. But if he gets it right, if the weld holds, if the doubled armor does what the calculations suggest it should, then maybe, just maybe, the 5 men who climb into this Sherman tomorrow morning will come back alive. The problem began not with engineering failure, but with doctrine. When the United States Army Ordnance Department designed the M4 Sherman medium tank in 1941, they built it to a specific operational philosophy. American armor doctrine emphasized speed, reliability, and combined arms tactics. The Sherman wasn't supposed to fight German heavy tanks in direct engagement. That's what tank destroyers were for. The Sherman's role was infantry support, exploitation, and rapid maneuver through enemy rear areas. The Sherman excelled at these missions. Its 500 horsepower Ford GAA 5.8 engine provided exceptional reliability. Its suspension could traverse terrain that immobilized German Panthers. Its logistics chain, standardized across 11 different manufacturing facilities, meant that damaged Shermans could be repaired and returned to combat faster than any other Allied tank. By 1944, American factories produced over 2,000 Shermans monthly. This industrial supremacy gave American armored divisions numerical advantages that German forces, operating with far fewer tanks and chronic fuel shortages, simply could not match. But doctrine collided with reality in the hedgerows of Normandy. German defensive tactics, refined through 3 years of combat on the Eastern Front, positioned 88mm anti-tank guns and heavy tanks in carefully prepared ambush positions. The Panzer VI Tiger, with frontal armor exceeding 100mm thick and sloped at compound angles, could engage Shermans at ranges exceeding 2,000 meters. The Panzer V Panther, introduced in July 1943, featured sloped armor equivalent to 140mm of effective protection on its glacis plate. At typical combat ranges of 500 to 1,000 meters, Standard Sherman 75mm guns could not reliably penetrate either tank from the front. The casualties reflected this disparity. During the Battle of Villers-Bocage on June 13, 1944, a single Tiger tank commanded by SS Obersturmführer Michael Wittmann destroyed 14 Sherman tanks and 15 unarmored vehicles in approximately 15 minutes. At the Battle of Aracourt in September 1944, the 4th Armoured Division's Combat Command lost 48 Shermans over 3 days of fighting against German Panther battalions. Crew survival statistics from the European theatre showed that when an 88mm armour-piercing shell penetrated a Sherman's fighting compartment, crew fatalities averaged 72%. Tank crews understood the mathematics of their vulnerability with terrible clarity. Lieutenant Belton Cooper, an ordnance officer with the 3rd Armoured Division, documented the psychological impact in his after-action reports. Crews knew that German tanks could kill them at ranges where their own guns were ineffective. This knowledge created what military psychologists later termed anticipatory trauma, a constant awareness of mortality that affected combat performance even before engagement began. The improvised solutions appeared almost immediately. In June 1944, within weeks of the Normandy landings, Sherman crews began welding sandbags to their tanks. The logic seemed sound. Sandbags stopped bullets. Surely they would provide some protection against shaped charge weapons like the German Panzerfaust and Panzerschreck. Tank battalions constructed elaborate steel frameworks, welding them to hull sides and turrets to hold sandbags in place. Some units stacked bags 4 deep on frontal plates, adding over 2,000 pounds of weight to vehicles already operating near their design limits. On March 9, 1945, officers from the 1st Armoured Group conducted the only systematic test of sandbag effectiveness. They positioned an M4A3 Sherman, fitted with standard sandbag armour at various ranges and angles, then engaged it with captured Panzerfaust 60 anti-tank grenades. The results destroyed the prevailing assumptions. When fired at the Sherman's side armour, the Panzerfaust projectiles blew away the sandbags and penetrated the underlying armour with no measurable reduction in effectiveness. When fired at an angle against the frontal plate, some shots failed to penetrate, but post-test analysis showed this resulted from the Sherman's existing sloped armour, deflecting the projectiles, not from the sandbags providing additional protection. Patton, informed by his ordnance officers that sandbags offered no real protection, while adding weight that strained suspensions and increased fuel consumption, issued his ban in summer 1944. The directive was unambiguous: no sandbags, no concrete, no improvised armour that added weight without providing genuine ballistic protection. Crews who violated the order faced disciplinary action. But the problem remained. German heavy tanks continued killing Shermans at ranges where American guns could not effectively return fire. The M4A3 Sherman Jumbo offered a solution, featuring 38mm armour plates welded to its glacis for a play, total thickness of 102mm, and effective protection exceeding 150mm. Only 254 Jumbos were built at the Fisher Tank Arsenal between May and July 1944. They arrived in Europe in September and October, distributed across multiple divisions. Their performance proved exceptional. From the front, the Jumbo could withstand Tiger I 88mm guns at all but point-blank range, but with fewer than 300 in theatre by December 1944 and over 4,000 standard Shermans requiring protection, the Jumbo couldn't solve the larger problem. The Battle of the Bulge changed everything. On December 16, 1944, German forces launched Operation Wacht am Rhein, a massive counteroffensive through the Ardennes forest. The assault involved over 400,000 German troops, including multiple panzer divisions, equipped with Tiger II heavy tanks. The Königstiger, or King Tiger, represented the apex of German armour development. Its frontal armour exceeded 180mm of effective thickness. Its 88mm KWK 43 litres 71 gun could penetrate Sherman armour at ranges approaching 3,000 metres. American tank crews faced technological supremacy they simply could not match with existing equipment. In the desperate fighting around Bastogne, Sherman battalions supporting the encircled 101st Airborne Division recorded loss rates exceeding 40%. When Patton's Third Army executed its 90-degree pivot north to relieve Bastogne, his armoured spearheads took devastating casualties from German ambush positions. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. On January 3, 1945, Patton convened a meeting of his ordnance officers and maintenance battalion commanders. The agenda was simple: find a solution to the armour problem. Find it fast. The conversation that followed would transform American tank survivability for the remainder of the European War. Major Wesley Hogan, commander of the Third Army's 1st Maintenance Battalion, presented data his unit had compiled from battlefield salvage operations. By early January 1945, the European theatre contained an abundance of destroyed Sherman tanks. Some had been knocked out by enemy fire, but retained intact armour sections. Others were victims of mechanical breakdown, mines, or abandonment during the retreat from the Bulge. Hogan's crews had been cataloguing this material, and the numbers were striking. Approximately 400 wrecked Shermans sat in salvage yards across Luxembourg and eastern France. Many featured the improved large hatch hull design with frontal glacis plates 2.5 inches thick at 47 degrees, providing substantially better protection than earlier Sherman variants. These plates, cut free from destroyed hulls, could be welded onto operational tanks as appliqué armour. The mathematics were compelling. A standard M4A3 Sherman with 2-inch frontal armour at 56 degrees offered 77 millimeters of line-of-sight thickness. Adding a salvaged 2.5-inch plate to the front would create a total of 4.5 inches of steel at angle. The effective protection would jump to approximately 130 millimeters, matching the jumbo's frontal defense. If welded at a slight standoff distance, creating an air gap between the original armor and the added plate, the configuration might offer even better resistance to shaped charge weapons by forcing premature detonation of the warhead's jet. Patton listened to Hogan's presentation, then asked the question that would define the program. Can your men weld that thick? Can they do it in field conditions? And will the welds hold under combat stress? The answer required understanding the metallurgy and welding technology of 1945. Sherman armor consisted of rolled homogeneous steel, a carefully balanced alloy that combined hardness with ductility. The specific composition included carbon for hardness, nickel for toughness, chromium for wear resistance, and molybdenum for high-temperature strength. This balanced approach prevented the armor from being too brittle, which would cause shattering under impact, or too soft, which would allow excessive penetration. Welding armor plate presented significant technical challenges. The high carbon content, typically around 0.4%, made the steel prone to cracking during the welding process. When heated to welding temperatures exceeding 1500 degrees Celsius, then rapidly cooled, the steel's microstructure could transform into brittle martensite. Cracks would propagate through the weld and into the base metal, creating weak points where armor-piercing shells could catastrophically defeat the protection. Standard welding procedures for armor plate, documented in Army Technical Manual TM 9-2000, 860, required specific protocols. Preheat the base metal to between 150 and 200 degrees Celsius to reduce thermal shock. Use low hydrogen electrodes to prevent hydrogen embrittlement. Maintain strict interpass temperatures during multi-pass welding. Post-heat the completed weld to relieve internal stresses. These procedures worked well in factory conditions with controlled environments and specialized equipment. Field welding in January 1945 offered none of those advantages. Maintenance battalions operated from tents and hastily constructed workshops. Temperatures regularly dropped below freezing. Portable generators provided inconsistent power for welding equipment. The plates being welded were salvaged from combat losses, often damaged by shell impacts, warped by fire, contaminated with rust and debris. Yet, Hogan believed his welders could make it work. The key was using nickel-based electrodes rather than standard steel rods. Nickel, with its lower carbon equivalent and superior ductility, produced welds that remained tough even when applied to high-carbon armor steel. Army Welding Specification, MILE 22200A, called for electrodes, containing between 18 and 25% nickel for armor applications. These electrodes were expensive, required careful storage to prevent moisture absorption, and welded more slowly than standard rods. But they worked. Hogan's most experienced welder was Staff Sergeant Frank Kowalski, a first-generation Polish immigrant from Pittsburgh who had spent 8 years working in steel mills before the war. Kowalski understood metal at an intuitive level that formal engineering training couldn't replicate. He could read a weld by its color, judge steel temperature by the spectrum of light it emitted, hear problems in the arc's characteristics before visual inspection revealed them. Patton approved the program on January 5, 1945. General Order No. 47 authorized maintenance battalions to salvage armor from destroyed tanks and weld it onto operational vehicles. The order specified that approximately 36 up-armored Shermans should be supplied to each of the 3 armored divisions in 3rd Army, with priority given to tanks serving as platoon and company lead vehicles. The modifications would focus on the frontal glacis, the most frequently hit area in combat engagements. The first conversion began on January 10th in a Quonset hut workshop outside Metz. Kowalski and his 4-man crew started with a nearly new M4, a 376mm Sherman that had seen only 3 weeks of combat. The tank's frontal armor showed impact scarring from small arms fire but no penetrations. The crew had survived. That was about to change if they couldn't get better protection. The salvaged armor came from another M4, a 3. This one destroyed during the defense of Bastogne. An 88mm armor-piercing shell had struck the right sponson, penetrated into the ammunition stowage, and caused a catastrophic fire that killed the entire crew. The frontal glacis remained intact, a single forged plate 2.5 inches thick, angled at 47 degrees. Kowalski's crew used cutting torches to separate it from the destroyed hull, then ground away the damaged edges and cleaned the surface in preparation for welding. Positioning the salvaged plate required careful calculation. Welding it directly onto the Sherman's existing glacis would create a tight bond with no air gap, maximizing the total steel thickness but potentially creating stress concentrations at the weld joint. Alternatively, mounting the plate with a small standoff distance, perhaps an inch or 2, would create spaced armor that might offer better protection against shaped charge weapons while reducing stress on the plate welds. Kowalski chose a compromise. He welded steel spacers at the top and bottom edges of the glacis, creating a 1-inch gap between the original armor and the added plate. This configuration served multiple purposes. The air gap would potentially disrupt shaped charge jets. The standoff reduced direct thermal transfer to the base armor during welding, minimizing heat stress. And if the added plate took a direct hit that caused cracking, the damage might not propagate into the tank's structural armor beneath. The welding process took 11 hours spread over 2 days. Kowalski preheated the weld areas using a torch, bringing the metal to approximately 150 degrees Celsius, hot enough to touch bare-handed for only a second. He used Lincoln Shield Arc nickel electrodes, 3/16 of an inch in diameter, running at 140 amperes with direct current electrode positive polarity. Each pass of the electrode deposited a bead of weld metal, approximately 3/8 of an inch wide. The added plate required continuous welding around its entire perimeter, roughly 18 linear feet of weld, applied in multiple passes to build up sufficient thickness and penetration. The arc temperature exceeded 6,000 degrees Celsius, where the electrode tip contacted the steel. This extreme heat created a molten pool, approximately an inch in diameter, that flowed and solidified as Kowalski moved along the joint. The nickel-based weld metal, glowing white-hot during application, cooled to a silvery grey finish that contrasted visibly with the darker base steel. Kowalski maintained strict control of his travel speed, approximately 4 inches per minute, fast enough to prevent excessive heat buildup, slow enough to ensure complete fusion between the weld metal and both pieces of armor plate. Between weld passes, he allowed the metal to cool naturally, checking temperatures with a surface pyrometer to ensure interpass temperatures stayed below 250 degrees Celsius. Cooling too quickly would cause cracking. Maintaining too much heat would alter the steel's grain structure, reducing toughness. The balance required constant attention and judgment that came only from years of experience. On January 14th, with the welding complete, Kowalski's crew used an angle grinder to smooth the weld beads, creating a more aerodynamic profile that might help shells glance off rather than achieving perpendicular impact. They painted the entire assembly with olive drab to match the tank's existing finish, though the slightly different texture of the added plate remained visible to close inspection. The modified Sherman, now carrying 4.5 inches of frontal armor at 47 degrees, offered effective protection equivalent to 130 millimeters of line-of-sight thickness. On paper, this matched the factory-built jumbo. The critical question remained unanswered. Would field-welded, appliqué armor, applied under improvised conditions with salvaged plates, actually survive combat? Or would the welds fail under the shock of high-velocity impacts, turning the added protection into deadly shrapnel? That question would be answered 9 days later in a snow-covered field outside the German village of Hufeleis, January 23, 1945. The temperature has dropped to -12 degrees Celsius. First Lieutenant Robert Chen commands a platoon of 5 M4A3 Shermans from Company B, 37th Tank Battalion, 4th Armored Division. 3 of his tanks carry the new field-welded armor modifications. 2 retain standard protection. Chen didn't request this arrangement. 3rd Army Ordnance officers distributed the up-armored vehicles based on tactical position. Lead tanks got priority. Chen's tank, call sign Baker 26, leads the column. The mission is reconnaissance in force toward Hufeleis, a Belgian town the Germans have fortified as a critical road junction. Intelligence reports indicate the presence of at least 2 Tiger tanks and multiple Panther medium tanks supporting German infantry positions. The 4th Armored Division's advance has stalled for 3 days against this defensive line. Chen's platoon is probing for weak points, attempting to identify enemy positions without triggering a full engagement. The terrain offers no advantages. Open fields provide clear lines of sight for German anti-tank guns. Tree lines along the ridges conceal enemy positions. Fresh snow, 6 inches deep, slows movement and leaves obvious tracks. Chen advances cautiously, watching for the telltale muzzle flash that precedes an 88mm shell by microseconds. The first shot comes at 0843 hours from a concealed position approximately 900 meters northeast. The distinctive crack of a German 8.8 cm KWK 36 gun echoes across the valley. Chen's driver, sensing the shot before conscious thought, throws the Sherman into a hard turn. The armor-piercing shell, travelling at approximately 810 meters per second, crosses the distance in just over 1 second. It strikes Baker 26's frontal glacis at 28 degrees from perpendicular. This is the moment that validates or condemns months of field improvisation. The shell impacts the outer appliqué armor plate first, striking it with kinetic energy exceeding 3 million joules. The hardened steel penetrator, designed to punch through homogeneous armor, begins its work. But the plate's angle and the air gap behind it change the physics of penetration in ways German gunners haven't accounted for. The shell penetrates the outer plate, consuming energy in the process. The penetrator, now slightly deformed and tumbling from the angled impact, crosses the 1-inch air gap. It strikes the Sherman's original frontal armor at a changed angle, no longer perpendicular but skewed further by the deflection from the first plate. The combined thickness of 4.5 inches of steel at compound angles proves sufficient. The penetrator stops, embedded in the inner armor plate, 3/4 of the way through but not breaching the crew compartment. Inside Baker 26, the impact sounds like a massive hammer striking a steel drum. The entire tank rocks backward from the kinetic energy transfer. Metal fragments from the shell's penetration of the outer plate ricochet inside the gap between armor layers, their energy dispersed. Chen's gunner, Corporal James Morrison, locates the Tiger's muzzle flash and fires in response. The Sherman's 76mm M4A3 gun sends an armor-piercing shell downrange. The round misses, impacting the frozen ground 20 meters left of the Tiger's position. The Tiger fires again. This shot strikes the turret side, penetrating the 2-inch armor and killing the loader instantly, but Chen's tank survives, mobile and capable of returning fire. In the calculus of armor, warfare, this represents victory. A standard Sherman, hit twice by Tiger main gunfire at under 1,000 meters range, would be a burning wreck with total crew loss. Baker 2-6 withdraws under cover fire from the other platoon tanks, 1 crew member dead but 4 surviving, the tank damaged but recoverable. The after-action reports from this engagement reached Patton's headquarters on January 24th. Major Hogan's analysis noted the critical details. The field-welded applique armor had survived a direct hit from a Tiger 88mm gun at 900 meters range. The welds held. No catastrophic failure. No spalling that endangered the crew beyond the normal risks of combat. The added protection had saved lives. Patton's response was immediate. General Order No. 52, issued January 26, 1945, expanded the armor modification program. Every maintenance battalion in 3rd Army received authorization to convert Shermans using salvaged armor. The target increased from 36 vehicles per armored division to 100. Priority expanded beyond lead tanks to include any Sherman in frontline service. Where salvaged American armor proved insufficient, crews could use German armor plate captured from knocked-out Panthers and Tigers. The industrial logistics of this expanded program revealed both American material abundance and tactical desperation. By late January 1945, 3rd Army controlled salvage yards containing over 800 destroyed or damaged Sherman tanks. Maintenance battalions established assembly line procedures for armor recovery. Cutting crews used acetylene torches to remove intact glacis plates, turret faces, and side armor sections from wrecked hulls. Transport units moved the salvaged plates to forward workshops. Welding teams, now expanded to include any soldier with metalworking experience, worked 16-hour shifts, applying armor to operational tanks. Sergeant Kowalski trained welders at a rate that would have been impossible in peacetime. His crash course in armor welding lasted 3 days. Day 1 covered electrode selection and proper arc characteristics. Day 2 focused on joint preparation and fit-up procedures. Day 3 involved supervised practice on scrap plates before attempting work on actual combat vehicles. This abbreviated training produced welders whose skills were narrowly focused but sufficient for the specific task. They learned to weld armor plate. Nothing more. It was enough. The quality control process relied on visual inspection and basic testing. Kowalski, or another experienced welder, examined each completed modification, looking for cracks, incomplete fusion, porosity, or other defects that would compromise strength. Welds that failed inspection were ground out and redone. Approximately 8% of initial welds required rework, a surprisingly low failure rate given the improvised conditions and abbreviated training. The first 100 conversions were completed by February 7, 1945. These modified Shermans went immediately to frontline units preparing for operations to cross the Rhine River. Tank commanders who received the up-armored vehicles reported improved crew confidence and willingness to accept lead positions in column advances. The psychological impact of better protection proved as significant as the actual ballistic improvement, but the program's expansion created unexpected complications. The added armor increased Sherman combat weight by approximately 1,700 pounds, bringing total mass to just over 36 tons. This additional weight stressed suspensions, designed for a lighter vehicle. Front bogie units, carrying the increased load from the frontal armor additions, experienced accelerated wear. Transmission gears, particularly first and second gear sets, showed increased failure rates during prolonged operations. More critically, the weight distribution changed the Sherman's ground pressure and mobility characteristics. On soft ground, frozen mud, or deep snow, the heavier Shermans occasionally bogged down where standard vehicles could traverse. Tank commanders learned to avoid marginal terrain that would have been passable before modification. This tactical constraint sometimes forced units to choose between better protection and better mobility, a compromise no one welcomed. The welding process itself created vulnerabilities that combat experience gradually revealed. When an 88mm armor-piercing shell struck near a weld joint, the impact's shockwave could propagate through the weld metal differently than through base steel. In approximately 12% of documented hits near weld areas, cracking occurred that required repair before the tank could return to combat. This failure rate, while manageable, reminded maintenance crews that field modifications couldn't match factory-produced armor in structural integrity. German forces adapted their tactics as the up-armored Shermans became more common. Intelligence reports captured from Wehrmacht units in March 1945 included specific instructions for engaging modified American tanks. Anti-tank gun crews received orders to target turrets and hull sides rather than heavily protected frontal areas. Tiger and Panther commanders were instructed to seek flank shots and avoid frontal engagements with visibly modified Shermans at ranges under 800 meters. This adaptation demonstrated both the modification program's success and its limits. The added frontal armor changed German tactical behavior, forcing them to attempt more difficult shots and reducing their effectiveness. But it didn't make Shermans invulnerable. Tank crews understood that the welded plates bought them a chance to survive the first hit, perhaps the second. Beyond that, survival depended on crew skill, tactical positioning, and the same factors that had always determined armor combat outcomes. The American advance accelerated through February and March 1945 as German defensive capabilities collapsed under overwhelming Allied pressure. Third Army crossed the Rhine on March 22 near Oppenheim, executing the river crossing with fewer casualties than anticipated. The up-armored Shermans, concentrated in lead companies of armored battalions, played a documented role in this success. After-action reports from the 11th Armored Division noted that modified Shermans absorbed hits that would have destroyed standard vehicles, maintaining the momentum of attacks that might otherwise have stalled under German anti-tank fire. By April 1, 1945, 3rd Army maintenance battalions had completed modifications on over 220 Sherman tanks. The program expanded beyond Patton's forces as other armies adopted similar procedures. 1st Army, 7th Army, and 9th Army Ordnance units began their own armour salvage and modification operations. The technique spread to British forces, though they focused primarily on upgunning Shermans with 17-pounder guns rather than armour improvements. The total number of field-modified, up-armoured Shermans operating in the European theatre by war's end exceeded 400. This represented approximately 3% of Sherman's strength in theatre, a small proportion that nonetheless had disproportionate impact. The modified tanks served primarily as platoon and company lead vehicles, absorbing the most dangerous positions in tactical formations. Their enhanced survivability allowed aggressive tactics that would have been suicidal with standard protection. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Casualty statistics from units operating modified Shermans revealed measurable improvements in crew survival. The 3rd Armoured Division, which operated 63 up-armoured Shermans between February and May 1945, compiled comparative data. Crews in modified tanks experienced crew fatality rates of approximately 41% when their vehicles were knocked out by enemy fire. Crews in standard Shermans facing the same threats experienced crew fatality rates of 68%. The difference, 27 percentage points, represented lives saved by field improvisation and skilled welding. Lieutenant Chen survived the war. His tank, Baker 26, took 3 more hits before Germany's surrender on May 8, 1945. 2 of those hits penetrated the appliqué armour but were stopped by the underlying plate. The third struck the turret, killing Chen's replacement loader, but leaving the rest of the crew alive. Chen credited Kowalski's welds with his survival, a sentiment echoed by dozens of other tank commanders whose crews benefited from the armor modification program. Sergeant Frank Kowalski welded armor modifications on 37 Sherman tanks between January 10th and April 20th, 1945. He trained 48 other welders in the techniques required for field armor application. His work was never officially recognized with awards or commendations. The Army didn't publicize field modifications that highlighted standard Sherman vulnerabilities. Kowalski mustered out in November 1945 and returned to Pittsburgh, where he worked in steel fabrication until his retirement in 1973. He died in 1988 at age 71, largely unknown outside the community of Sherman tank veterans who remembered his contribution. General George Patton's role in authorizing and expanding the armor modification program receives mixed historical assessment. Some military historians credit him with pragmatic innovation that saved American lives. Others note that he was responding to problems created by his own earlier ban on field modifications and by Army ordnance's failure to provide adequately protected tanks for the missions Third Army was tasked to accomplish. Both interpretations contain truth. Patton operated within constraints imposed by industrial capacity, shipping limitations, and strategic priorities that favored quantity over quality in tank production. The Sherman tank's reputation remains contentious among military historians and veterans. It was simultaneously too lightly armored to face German heavy tanks in direct engagement and the only Allied tank available in sufficient numbers to win the war. Its reliability, ease of maintenance, and superior logistics made it strategically superior to German armor, despite its tactical inferiority in one-on-one engagements. The field armor modifications represented desperate improvisation to address real vulnerabilities, but they also demonstrated American flexibility and willingness to adapt under combat conditions. The technical lessons from the modification program influenced post-war armor development. The United States Army's post-war tank design studies, compiled in 1946 and 1947, extensively analyzed the effectiveness of appliqué armor and spaced armor configurations. The M4A3 Patton tank, entering service in 1952, incorporated design features directly informed by wartime modification experience. Its turret featured spaced armor with an air gap similar to the improvised Sherman conversions. Its glacis plate used compound angles that had proven effective in deflecting armor-piercing projectiles. The welding techniques developed under field conditions also advanced post-war capabilities. The Army's revised armor welding specifications, published as TM 9 to 237 inches, 1948, incorporated procedures validated during the Sherman modification program. The use of high-nickel electrodes for armor applications became standard doctrine. The procedures for field repair of combat-damaged armor drew directly from techniques developed by maintenance battalions in Europe during 1945. By 1950, only 43 of the field-modified, up-armored Shermans remained in U.S. Army inventory. Most had been scrapped during the post-war drawdown. A few served in training roles or were transferred to Allied nations through military assistance programs. None survive today in museums or private collections. The improvised nature of the modifications and the lack of documentation meant that post-war preservation efforts focused on factory-standard examples rather than field-modified variants. The human cost of Sherman tank operations in World War II remains stark. Of the approximately 50,000 Shermans deployed to the European theatre, over 18,000 were knocked out by enemy action. Crew casualties totaled approximately 36,000, killed or wounded. These numbers reflect the reality that no amount of armor modification could eliminate the fundamental risks of mechanized combat. But within those statistics, hundreds of men survived hits that would have killed them without the added protection of field-welded armor plates. The physics of armor penetration haven't changed since 1945. Kinetic energy projectiles defeat armor through a brutal calculation of velocity, mass, and material properties. The improvised modifications didn't change these fundamental principles. They simply added enough thickness and complexity to shift the balance from certain penetration to possible survival. In the milliseconds after an 88mm shell struck a Sherman's glacis, those additional inches of steel made the difference between a catastrophic kill and a damaged but survivable hit. Sergeant Kowalski's contribution represents a category of wartime innovation that receives little historical attention. He didn't invent a revolutionary weapon. He didn't develop a catal, new tactical doctrine. He applied existing welding knowledge under difficult conditions to solve an immediate problem. His skill turned salvaged armor plates into life-saving protection. His training allowed dozens of other welders to replicate his work. The cumulative effect of these individual actions saved lives that would otherwise have been lost. The story of Sherman armor modifications illuminates a paradox at the heart of industrial warfare. The United States possessed the manufacturing capacity to build over 50,000 tanks. American factories could produce steel, engines, weapons, and ammunition at rates that overwhelmed German industry. But that same industrial system couldn't adapt quickly enough to provide optimal protection for the crews who operated those tanks. The gap between production capability and tactical requirements was filled by field improvisation, soldiers with welding skills, and commanders willing to authorize modifications that weren't in any manual. The final up-armored Sherman rolled out of a Third Army maintenance workshop on April 28, 1945, 1 week before Germany's unconditional surrender. The war in Europe was effectively over. The modifications that had seemed so critical in January were suddenly obsolete. The tank, serial number 3067293, served briefly in occupation duty, then was shipped to a depot in France and eventually scrapped in 1947. No record remains of the welder who applied its armor or the crew who benefited from that protection. But in a broader sense, the legacy of the armor modification program extended far beyond the specific tanks it produced. It demonstrated that effective armor protection required attention to angles, spacing, and material properties rather than simple thickness. It proved that field modifications, properly executed, could address serious vulnerabilities without waiting for factory production, and it showed that individual skill and initiative, applied at the tactical level, could save lives even when strategic and industrial systems failed to provide adequate solutions. The German Tiger commander who fired the shot that struck Lieutenant Chen's tank on January 23, 1945, probably never knew his shell failed to achieve a kill. From 900 meters distance, through morning mist and gun smoke, the difference between a catastrophic penetration and a deflected hit might not be visible. He would have reported engaging an American Sherman, claimed a probable kill, and moved to his next firing position. The survival of Baker 26's crew remained unknown to him, as did the reason for that survival. That reason was 48 feet of Weld metal, applied by a Pittsburgh steelworker in a freezing workshop outside Metz. It was nickel-rich electrodes designed for armor applications, used according to specifications that were improvised as much as engineered. It was salvaged armor plates cut from tanks, whose crews hadn't survived, given new purpose in protecting crews who still had a chance. It was the accumulated skill of thousands of welders, working in conditions that would have invalidated any warranty, creating protection that saved lives one tank at a time. The mathematics were always simple. Add thickness, improve angles, create space that disrupts penetrators. The execution was never simple. It required skill, judgment, adaptation, and the willingness to try techniques that weren't officially approved because men were dying and something had to be done. The success of Sherman armor modifications wasn't a triumph of engineering or doctrine. It was a triumph of practical problem-solving by people who understood that perfect solutions weren't available and good enough solutions might keep crews alive. In the final analysis, the story of how field-welded armor changed Sherman's survivability is a story about the distance between theory and practice in mechanized warfare. Military planners in 1941 designed the Sherman for specific missions based on doctrinal assumptions that combat in 1944 and 1945 proved inadequate. The crews who fought in those Shermans couldn't wait for new tank designs to enter production. They needed protection immediately. Maintenance battalions, ordnance officers, and skilled welders provided that protection through improvisation that military regulations never anticipated and official procurement systems couldn't have delivered in time. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.